So now I will have a quick software demonstration in which I'll show you how we can extract the individual modal responses while performing the response spectrum analysis of the buildings. Generally, we know that for performing the response spectrum analysis, we have to provide this curve as an input, which is the spectral acceleration versus time period. If the purpose is to design a structure, this curve will come from a standard building code which you will be following for the purpose of structural design. If the purpose is to evaluate the response of a structure under a particular earthquake, this relationship should be the spectral acceleration versus time period for that particular earthquake. Obviously, for real earthquake, it would not be that smooth, it will be an irregular shaped spectrum. So depending upon what is the purpose of your analysis, you will give this curve as an input, and then program calculates the equivalent static forces for each mode. Fi vector for each ith mode applies that vector as a static force vector, and then determines the response, for example Ri for each mode, any ith mode, and then combine those responses in a either using SRSS or CQC to get the overall peak response. But that response will essentially be static because the equivalent static forces are not the dynamic forces, they are the peak estimates of those dynamic forces, so they are static. But the program directly provides you this combined response. It doesn't provide you the response for each mode individually. So in this particular demonstration, I'll show you how you can use CSI ETABS to get the individual modal peak responses. Obviously, they will not be the fluctuating responses, not dynamic, but static responses. So for example, if after the analysis, the program tells me that, okay, this is the, let's say, story displacement along the height. This is the height axis, and let's say this is the displacement axis. So I can see that at different floors have different displacements, but I can actually decompose that into how much of these displacements are coming from first mode, how much from second mode, and how much from the third and higher modes, for example. So in this demonstration, we will see how we can extract or get the individual modal responses from the RSA. So we already know that combined response is available directly, but how we can extract the responses for each mode individually. So I'll be actually using an example structure for this demonstration. Let me open that example structure. So this is a 44-story reinforced concrete building, and it is having a core wall and also some planar walls, and it has reinforced concrete columns, beams, as well as reinforced concrete shear walls. So it has a total height of 140.8 meters, and let's say that we want to perform its response spectrum analysis. So I'll quickly show you all the steps. After completing your model and everything, obviously the very first step should be to define a response spectrum curve. So you will be going to define functions and response spectrum, and here you can see that there is already a response spectrum which is defined. I can modify it, and actually it was defined from a text file, so therefore it is currently not showing. Maybe this one, yeah, this one is from a UBC 97, an old code, but the curve is available here. If you want to define it yourself from any particular building code equation, you can select that particular code and add new function, give the parameters which are used in the equation of that design spectrum equation, and then it will plot it for you. So it can have different view options, as well as you can convert it into user defined. So for this particular demonstration, I already have one response spectrum which is defined. The next step should be to go to load cases and import that particular response spectrum curve and define it as a load case. A lone definition of the function won't be enough. Obviously you have to run the analysis, and for that you have to define a load case. So I already have a load case called RSX, which is the response spectrum type load case. I can just quickly show you by modifying it, and you can see here that it has a response spectrum type of analysis, and in that it is in applied in the u1 direction, and the function is, let's say, rs. Maybe we can select UBC97, which is already defined, and then if you want to apply a scale factor to that, obviously if you want to apply code factors, you can incorporate them in place of this scale factor. And also if your original response spectrum is in the G units, and your actual acceleration is, let's say, in millimeter per second square, the actual conversion factor from G to millimeter per second square should be applied here as a scale factor. Obviously the response spectrum analysis will be using the idea of mode shapes and time periods. So which modal load case should be used to calculate mode shapes and get time periods, and then the modal combination rule, SRSS or CQC, whatever you want. If you want to apply response spectrum in two different directions in the same load case, then you have to define a directional combination also, and also you have to define the damping. It is currently 5% constant modal damping for all modes, uh, and you can see other options, for example mass proportional or stiffness proportional damping. And then if you want to apply a diaphragm eccentricity, you can modify it here and apply an eccentricity here. Otherwise the forces will be applied at the center of diaphragm masses. So with this we will be simply defining a particular response spectrum case. In this example it is only the x direction response spectrum. So when we run the response spectrum analysis now, we will be only getting the combined response. For example, let me open the same model which is run already with this RSX load case and show you some of its results. So let me just open the same model, but this time it is run already. So let me just open that model and then show you some of its results. For example, let's see the story response plots from display menu, and in here we can select the any response type, for example maximum story displacement, and the case we can select as RSX, which is our case, this one. So you can see here that since the response spectrum was applied primarily in x direction of the building, so therefore the story displacement in x is shown here. It is around you can say some 1350 millimeters, or you can say 1.35 meters. Actually it is uh, quite high, but the building is also 44 story. So you can see what drift, roof drift, it can be converted into by dividing this peak number by the height of the building. So this is a combined displacement now. It is contributed by many vibration modes. The program by default doesn't show us that how much of this displacement profile is contributed by first mode, how much second mode, and how much third mode. And this information is sometimes really important. For example, one of a very useful you can say application of uh, getting the information about individual modes contribution is if you want to control the dynamic response of this building and want to design a control measure. For example, if you want to design a damper or a tuned mass damper or a tuned liquid damper, for example, the modal contributions will tell you which mode is contributing the most and which mode need to be suppressed, and then looking at the mode shape along the height and response of that particular mode shape along the height, you can decide about what should be the optimum location of that particular damper or any control measure, and what frequency and time period it should be tuned to in order to optimally suppress the response. All of this information is can all of this decision making actually can be made easy or made convenient if you have the individual modal contributions or the composition of dynamic response with you. So this is a combined response from all vibration modes. Let me go quickly to define and the modal case. For example, in the load cases, there is a default modal case which was selected in that response spectrum. So I can modify it and I can see that it is calculating the 20 number of modes. So actually we can say that the program uh, is calculating by contributing 20 vibration modes, first 20. Obviously they will be for all directions. From those 20 vibration modes, maybe the x direction modes will be either 5 or 6 maybe. We can quickly check that also. For example, we can go to display and show tables, and in that we can go to analysis results, structure output, modal information, and then we can see the modal mass participation ratios, this one. So we can see that table to classify those mode shapes along the directions also. For example, here we can see that the first mode have a time period of 4.782 seconds, and it has a 72% contribution in the x direction and no contribution in y and z. So it is a primarily translational mode in x direction. So it is a fundamental sway mode in x direction. The second mode is the fundamental sway mode in y direction. The third mode is actually uh, the the torsional mode. You can see here, if I can go to that side. So it has the highest contribution, 0.73 here in the RZ, which means it is the first torsional mode. Similarly, the fourth mode, this one, again have a 13% contribution in X. So it has the second highest contribution in X, which means it is the second mode in X. Then this one is again torsional, and then sixth mode is the second mode in Y direction. We can confirm that from animations also. Let's say that I uh, select a plan view for this right figure, for this left figure, okay, and then here if I can visualize the first mode, if I can just plot the deformed shape for first mode, it will be simply the fundamental translation in x direction. So you would be seeing it swing in the x direction. So I can also animate this, or I can you can say plot it in 3 dimension also. For example, on the figure in right, let me just plot it in 3 dimensions, first mode. So you can see that it is having a translation in x. So I can even animate that one also. So you can see it will be having a translational shape of oscillation in x direction. Similarly, I can oscillate the fourth mode, it will be the second mode in that particular direction. Similarly, all other higher vibration modes I can animate. So now let's come back to our original topic, and that is how we can extract the individual modal responses from the same model now. How we can extract the response for first mode, second mode, third mode. And actually before demonstrating it in the program, I already have done it in an Excel sheet using manual calculations. So let me just show you how they look like, and then we can get them from the program. So let me just open that Excel sheet here for the same 44-story example building. And since the global responses like story displacement, story shear, story moments, you can calculate them manually if you have the mass matrix or the story masses. So I have done it manually, so let me quickly show you and then we'll directly go to the program again. So I have this spectral acceleration versus time period values for different damping ratios, but I'll only be using 5% for this example. These are the first 3 time periods in X direction of my 44-story building. I've just shown you first mode, second mode, third mode. Actually, they are the first mode, fourth mode, and sixth mode maybe. But in X direction, they are first, second, and third. So the spectral acceleration values and displacement values are picked from the response spectrum data which is available for this particular example. And then I started with getting the mode shapes from ETABS. You can extract the mode shapes from ETABS after running the modal analysis. Let me show you how. You can go to ETABS and then again the story response plots, and in that you can select the diaphragm center of mass displacements, and for modal case and mode number can be 1. So this shape actually is the first mode shape. Obviously the absolute values doesn't matter. You can normalize them such that their absolute value is 1, only their relative values matter. So this is the first mode shape. You can copy that data, you can copy it from in Excel and plot it yourself. Similarly, you can type mode 2 here, and this will be your second mode according to software numbering. Actually, it is the first mode in Y direction, so you can see that it is the fundamental sway in Y direction, red color. The third mode is a torsional mode. Fourth mode is again the second mode in X direction, so let me type 4 and see here that this is the second mode shape in the X direction. Similarly, sixth mode I think was the second mode in Y direction. So you can see this is the sixth mode. I type 6 and it becomes the second mode shape. So we can not only plot mode shape vectors, but also we can animate the structure in those shapes, and then later on can extract data and copy it. So this is what I have done here, that I have the story masses already. I have the first, second, and third mode shape extracted from ETABS. I'll use these and use the equation of response spectrum analysis to get the individual story responses for first mode, for second mode, and then towards the right I have the third mode, and I can plot them individually then. So I'll share this Excel sheet with you. You can see how I have used the response spectrum equations to convert the mode shapes and modal participation factors and story mass matrix and everything into individual story responses, like absolute story displacement or story displacements, interstory drift ratios, story shear, story moment, and equivalent static forces. For example, this one is column for equivalent static forces for first mode, for second mode, for third mode, and then these forces can be converted into story shear diagrams and story moment diagrams. So I'll directly go down and show you graphically how these responses look like. So this black color was my individual response spectrum, my curve which I use as an input for this analysis, this one. And then I have the first mode shape, second mode shape, third mode shape in X direction only, and this actually comes from ETABS. And they are normalized such that the roof number is set to 1 and all other values are normalized accordingly. Then these are the individual modal responses. These are the story displacements. You can see that the first mode displacement shown by green color is actually following the shape of first mode. Second mode displacement, third mode displacement. You can see from this graph that the maximum displacement, almost more than 90% contribution, is coming from first mode. This is the interstory drift ratios. Again, the first mode is contributing the most, but second and third mode also contribute significantly and you cannot ignore them. Third mode, again the story shears, you can see that first mode contribute the most, but second and third mode also contribute significantly. Since these values are absolute values, so therefore instead of going towards the negative side of the graph, they just again go back to the positive side. But this is not absolute, this is corresponding to the actual numbers, but story shear envelope is absolute values. So you can see a significant contribution from higher vibration modes. When we perform SRSS to the individual modal responses or any modal combination, we get the combined response. Now ETABS give us directly these combined responses, and that we can obtain from here. For example, I can go to my response spectrum load case and let's say plot story shear. This is maximum story, this is story shear option, and let me select the response spectrum analysis load case. So this is RSX, you can see here, and this will give me directly the combined story shear which I show you in the graph in Excel. So this number you can see here, this blue line, and this story shear is combined story shear. But I also have individual story shears from individual vibration modes. When I SRS them, I get this combined line. So our target now is to obtain these individual modal responses from ETABS directly. Here in this Excel sheet I calculated them manually, but you can get them from the program directly. Those were some of the responses were not absolute, for example displacement and moment, but here I just convert them to all positive signs, which means absolute values. So you can see here the first mode, second mode, third mode, and this time I added the combined line also. So in displacement you can see that almost 100% of the displacement is contributed by first mode only. The combined line and the first mode line are very close. But here you can see the combined line in inter-story drift ratio and the first mode line have some difference, and that difference is actually because of the contribution of second and third mode in this analysis. Similarly, story shear, you can see that if you only include first mode in the analysis you will get green line, but the combined response is actually higher than that, which is because of the second and third mode contribution. Same is for moment also. Along the height you will have an error if you don't include second and third mode in any analysis. This is the when you apply the code prescribed factors, then the elastic demands are converted into the design demands, and we will not go into that detail. So our target now is to obtain these individual modal responses from ETABS directly. So there is a short trick which I'll explain now. If you go to display and show tables, you will see that in the structure output and in the modal information, there is a last result called response spectrum modal info. So you can check that table and click OK, and this will generate a table which will tell you or give you 6 quantities for each mode. So let me just see here. So let's say this is first mode and it has its time period, damping ratio. Now these are the 6 additional quantities which is reported by the program because of response spectrum analysis. This is the spectral acceleration values which it picked from the spectrum. Since the response spectrum RSX was only applied in the x direction, so therefore only U1 acceleration is reported here, which is picked from the given response spectrum and converted into the units of this model, which is millimeter per second scale. But more importantly, you have a column called U1 amplitude. If you applied that response spectrum into U2 direction, you would also have it U2, and if you want U3, you could have that also. But currently you have U1 amplitude. Let's see what this amplitude is. So let me go back to my presentation and show you one additional thing here. So currently we are here, that we are in the display, show tables, analysis results, structure output, modal information, and then there is a table called response spectrum modal information. So these, it gives us 3 acceleration values and 3 modal amplitudes. We know this is spectral acceleration, but these modal amplitudes are actually the product of modal participation factor, which is the gamma I factor for any ith mode, and response spectrum acceleration, which is the spectral acceleration SAI for that ith mode, and then divided by the eigenvalue of the mode, which is omega square. So this whole thing is called the modal amplitude, and the purpose of this modal amplitude is that when it is multiplied by any modal response quantity, because there is a modal case already which is by default available in ETABS, and it is run even before gravity load analysis. So that case also reports all the responses. For example, displacement, velocity, shear forces, moments, everything. So what you can simply do is you can multiply those quantities with this factor or this amplitude, which is gamma I times SAI divided by omega I square. This quantity is called modal amplitude, and this can be simply multiplied by all the modal responses, modal case responses, and then those responses will become the individual modal contributions in the response spectrum analysis, right? So you can use simply the modal case and multiply it with the amplitude, and it will become that mode's individual modal responses. So this is the equation for particular displacement of any ith mode in response spectrum analysis. If we can rearrange it, we can see that this is a constant quantity and this is called the modal amplitude, modal response spectrum amplitude. So ETABS directly report this number to you. You can simply multiply it with the modal case. So these results will come from modal case. You simply multiply it with them and you get the corresponding response quantity of that particular mode. So this is response of ith mode, right? And this is the ith modal case result, and then this is the modal response amplitude for any ith mode. So you can do it for first mode, multiplied with all the responses of first mode, you get the first mode contribution in the response spectrum analysis. You do it for second mode, similarly third mode, and all that. And how we can automate this multiplication also, we can use the load combinations option. Load combinations, we know that they by default they are actually meant for the purpose of structural design, but what they effectively do is that they simply take the results of a particular load case. They take the results of a load case and then multiply it with the factor which you provide, which is the load factor. For example, 1.2 times the dead load. What we can simply do, we can define a new load combination where the load case can be set to modal, let's say for first mode, and then multiply the amplitude of the first mode, right? So this load case will load combinations will simply become the combination which gives us the response quantities of the first modal contribution in the response spectrum analysis. So let me show you quickly. I have done it, and I'll quickly show you how you can use this trick to determine the individual modal contributions. So let's say that my first mode in x direction in this particular example have an amplitude of this much millimeter, which actually translates into uh, 1759 meters, right? 1759 meters. So if I want to get the individual responses of mode 1, which is the first mode in x direction, I can simply go to uh, define and load combinations, and this you can even do after the analysis also. And you can define a new load combination. I have already defined it, and so let me just modify it. So I named it as RSAX mode 1, and the type is linear addition. Actually there is no required because we just simply want to multiply a scale factor. So the the unit in which we are actually we are measuring the displacement is meters. So I can see here at the bottom right that it is my current units are in meters. So I have to convert that amplitude into meters. So let me show you that amplitude again. It is actually 175 meters, 175 meters, right? So let me just go and then uh, go to define load combinations, and this was the one which I was defining. So here I give 175.969, and I have selected the case as modal and mode number 1. So this I just add. Let me just quickly show you how I can add another one. So for that again I'll add a new row, and then you can select this and then this one. So obviously here we just want one particular modal case to be multiplied with this 175 only. So this will be only thing which we will be doing, and then we click OK, and this will be defined. For second mode I defined another load combination, and this time I selected the same modal case, but this time it is mode number 4, and this is the number which is the modal amplitude for mode 4. So let me quickly go back and show you the modal amplitude from the same table for fourth mode, which is the second mode in x direction, and it will be you can see here that it is modal amplitude is 22.3 meters. So I just come back, define load combinations, and in the second mode I can see here that I have defined 22 point this. Similarly for the third mode in x direction, I know that the seventh mode actually is the third mode in x direction, and this was the corresponding modal amplitude, so I just use it as a scale factor and then I click OK. Now these three combinations are actually giving me the individual modal responses for the response spectrum analysis. So all the responses from these combinations I can extract now, and then I can plot them, and they will be similar to these responses. Actually they should be very close to or equal to these responses which I calculated manually. So for example, let's see the displacement responses. Story displacements, I can again go to display, story response plots, and maybe let me just cut the few ones. Okay, maybe, okay, this is the story response. I can now select, for example, the story displacement, and instead of case I will be selecting the combination, which is RSAX mode 1. So this is my combination, but I know that it is now giving me the first modes in x direction contribution of first mode. So this is my story displacement, which is around 1.3 meters, right, 1300 millimeters. So we can see here that our first mode is also somewhere close to that number. The second mode's peak displacement should be, if I go to absolute responses, maybe down here, the second one will be somewhere maybe 160 millimeters, and it have a shape of second mode. So let me go to ETABS now and select the RSAX mode 2, and this is the second mode shape now in x direction. Obviously there will be some negligible contribution in y direction, because obviously no mode is a pure translational mode with exactly zero contribution in the other direction. It may also have some contribution in the other direction, but again you can see that the shape is second mode shape, and the peak number at roof is somewhere around 160 millimeter, which is also in our case shown by the blue line. And then similarly third mode will have even less contribution in the displacement, and let me just confirm it. Select the third mode contribution, the corresponding combination, and you will see that it just have a contribution of maybe 45 millimeters in displacement, roof displacement, but the shape is like third mode, right? The ETABS also plot by default the absolute values. Otherwise this would have gone in the negative side and then again positive side, just like the actual third mode, just like this third mode. But since we are plotting the absolute value, so the minus sign also becomes positive in responses. Same for other types of story responses we can plot. For example, let's say story shear for first mode, story shear, and let's say select the first mode combination which we have just defined. So this is mode 1, for example. So this should show us the first mode's contribution in response spectrum analysis for first mode. So its shape looks like the first mode forces, how the shear produced by the first mode forces. Similarly, let me select the second mode, and then the shape should look like the forces, story shears produced by the second mode. And similarly third mode, also you can see that it will be shape will be the like the shears produced by the forces of third mode. But obviously these are now this time it's not absolute values, but here in the Excel sheet I am plotting the absolute values, so therefore all the values are positive side. So second mode and third mode this time do not have a negligible contribution but a significant contribution. Even in some stories you can even see, for example 30 plus, that the blue line is even higher than the green line, which means the second mode is having a even higher shear compared to the first mode. Similarly you can see other responses also. So and you can also save them and you can copy them and save in Excel and plot them yourself. So that's how, using this quick trick, you can extract the individual modal responses also from ETABS and plot the responses like this. Also you can also have the combined responses, and then you can also plot them together to see the composition of response. So you can see here in this figure that the solid line, the dark line is the combined response, but this is for first mode, second mode, and then this is the third mode, and the combined is the square root of the sum of squares for all three modes. You can also include fourth, fifth, sixth, as many number of modes as you want, but obviously for low rise or mid rise buildings only the contribution from second or third mode would be enough. But if your building is significantly taller, you may need to go to the fourth, fifth, or sixth mode also. So that's how you can uh, extract the individual modal responses.